So today topic will be on thermodynamics versus kinetics and how it is related. Although two things are different, still there is a very strong correlation. And thermodynamics it talks about initial state and final states, and kinetics it talks about the path or the how the process is occurring. So we'll learn what is the difference and how they are related. So if you see, thermodynamics is basically all about if it will occur or it will not occur. It will tell it will happen or it is not going to happen. So it just talks about the feasibility. So it always tells whether or not a process or a reaction can occur or not occur. So it talks about the possibilities. It is possible or not. So it's all about if. And so what if it is important that tells whether a process will occur or not, how it will be decided. Is there a decrease in free energy? Always thermodynamics criteria looks into the scenario that is there decrease in free energy? So look into the matter that decrease in free energy and is there is any chance of getting more stable things. So that is the important thing regarding thermodynamics. It always think about if it is possible or not, is this feasible or not. And it is basically applicable to a system which are in stable or sometimes metastable equilibrium. So thermodynamics always talks about a scenario where the equilibrium is there. Maybe it is very absolute stable equilibrium or it may be metastable equilibrium. But thermodynamics always looks into equilibrium. And if you want to understand that, always you have to take care of lowering the free energy. And another thing thermodynamics always care about, that is what is the driving force. Is there sufficient driving force is available. So sufficient driving force is required to enforce a favorable transformation. And that part we already discussed during the solidification process, that undercooling, degree of undercooling is very essential. And why it is essential, we understood. So thermodynamics is always talks about if it tells whether or not a process will occur or not based on the decreasing free energy. It also always applicable to the system is stable or metastable equilibrium condition, and also it talks about the sufficient driving force required or needed to enforce a favorable transformation. And if you see on the contrary towards the kinetics, then it is all about how things are happening, how processes are progressing, what will be the path. So it talks about how. So thermodynamics talks about if, or kinetics is just on the contrary, it talks about how. So how fast, how slow a process can occur. So it will tells you the rate, determine the rate. It also applicable to a system in a transition from non-equilibrium to equilibrium. So it talks about the transition of a system from non-equilibrium to equilibrium or between two equilibrium states. So it always talks about the path, the how the process is occurring, and applicable to a system in transition from non-equilibrium to equilibrium or between two equilibrium states if the transition is occurring. And thermodynamics of a process is generally or usually about how to overcome the energy barrier to finish the transformation from starting state to final state. If you are talking about reaction process, then reactant to product state. So here the process, how the path is going to take place, and during the path what will be the way and what will be the energy barrier, and how you are overcoming the energy barrier to finish a particular transformation from initial state to final state. All those things are under the purview of kinetics. So now we are understanding that thermodynamics or kinetics are having a futuristic difference, but they are really related. And if you look at thermodynamics, you have to understand the initial state, final state, and all the thermodynamic potential variables. And if you look at the kinetics, you have to understand transition state, driving force, and activation energy, all those things. So now we can discuss like that. Suppose a process concerned for kinetics could be a chemical reaction. Now we are taking an example of chemical reaction, change from different molecules of materials, or a transformation between two material structure. You can understand that is representing phase transformation, for which only the crystalline structure changes while the chemical composition remain the same. So one, there is a molecule or structure of the molecule or certain things are changing from reactant to product, that you can tell the chemical reaction. You want to understand what is the process involved with the chemical reaction, then you have to understand the kinetics. Or for a transformation between two material structure means their crystalline structure, you are not bothering about the change in chemical composition, then you are actually look into the phase transformation. So indeed, such phase transformation will be one of the major topic throughout this kind of kinetic subject, metallurgical kinetic subject, because in metallurgy, lot of phase transformation are going to happen. And if you are going to customize those phase transformation through heat treatment methods, then you are going to achieve different properties, desired properties for customized applications. But for application specific properties you want to achieve, then you have to go for heat treatment of certain heat treatable alloys like steel. So these kind of things, if you want to understand, then a phase transformation is a very important part, and associated kinetics also very important. And if you check certain example, phase transformation include fusing of water, eutectoid transformation of steel between austenite and pearlite. And pearlite is a mixture of alpha iron and cementite Fe3C, or transition from graphite and diamond. But it takes long time. Transition between graphite to diamond, that takes long time. So very slow process. So in all process transformation, atomic or ionic arrangement take place. So you can tell and you can understand that in all process of material transformation, there must be atomic or ionic rearrangement. The atomic or ionic rearrangement takes place during all the process of materials transformation. When an atom or ion moves in an environment surrounded by other atoms or ions, bonds are broken, new bonds are formed, and the surrounding atoms are displaced during the transition from their equilibrium positions. Actually, when an atom moves in an environment, and if you get the scenario, the neighboring lot of other neighboring atoms are there, and then what is going to happen? Certain bonds will break and certain new bonds will form. So you can tell that this kind of transformation associated with the bond breaking and new bond formation process. And this leads to a momentary increase in local energy, forming an intermediate or non-equilibrium state. So this bond breaking and bond formation, this kind of process, this kind of scenario can lead to a momentary increase, a temporary increase in local energy, and forming an intermediate or non-equilibrium state. And people can name that so-called transition state or activated state. So if you go for next slide, then you can understand. Here TS, T2, TS2, TS1, these are the activated state or transition state. And x-axis is reaction coordinate and y-axis is the energy. So now you can correlate previous 1 minute discussion that there will be a non-equilibrium state or transition state or activated state. So again I am repeating, materials transformation are basically atomic or ionic rearrangement. It's just rearranging, atomic and ionic rearrangement going to take place. And in order to get such kind of scenario, that kind of transition, what is happening? The bonds are broken and new bonds are formed. And these kind of phenomena leads to a temporary enhancement in local energy and forming an intermediate non-equilibrium state. And you can represent that state as a transition state or activated state. In the picture, you can see that. Thus, two equilibrium states which are characterized by local minima is in free energy. Suppose you see in the cheese, Stanford's Gibbs free energy are separated by maximum represented by activated state. You can see in that, in the scenario, that in the picture there is a activated state. Suppose you can see transition state 1 or transition state 2, whatever one plot. If you can concentrate on, then you can understand there will be a energy barrier and non-equilibrium state. So in thermodynamically, what we learn, that there will be a two state, and that is one starting state and another is final state. And thermodynamic always consider initial state and final state. It does not bother about the path, which will be the energy barrier in order to get that intermediate non-equilibrium state or transition state or activity state. Thermodynamic are not going to bother about that. Always bother about that. So now from the picture, if you want to understand that there is a starting state and there is a final state. In both the path, if you see one path having higher activation energy barrier, that is transition state 2, and one path having lower activation energy barrier, that is transition state 1. And that is due to catalyst. If you apply certain catalyst, then you can reduce the energy barrier. So that's why people used to tell that catalyst cannot start or initiate a process or reaction, but it can facilitate, it can help the process. How? Now, by reducing the activation energy barrier. So your transition state, that activated complex state, will be achieved at lower energy barrier, so that the process can be facilitated, can become ameliorated. It will be easy to get from starting state to final state through the lower activation energy barrier of transition state. And now if you look at a scenario where two final states are there and two transition states are there, such kind of scenario, the both kinetic control as well as thermodynamic control are different. Here you can see the final state also changing, and as well as the transition state activation energy barrier is also varying. So both the control, thermodynamic and kinetic control, are operative. So now you have to go for again the first picture, and for one plot from starting state to final state, in between that non-equilibrium activated or intermediate state, you have to concentrate. The local minima, in that case, you can say that this is a state function and intrinsic to molecular structure, where interatomic interaction that plays an important role in determining system energy. Now, the energy minima state you can generally can be calculated by certain theoretical or computational approach. But if you go for maximum or activated state for which the structure is not in equilibrium, then this kind of scenario, energy minimized state, you are not going to calculate easily, but it's not at all, you cannot calculate. Suppose for a process to occur, it must overcome the energy maximum. That barrier must overcome. This is the kinetic energy barrier. And the larger the barrier, the difference between the maximum and the initial minimum, the harder the process to occur. Means larger barrier means the difference between the maximum and the initial minimum. And then what will happen? The reaction will face harder to process in the forward directions. So harder the process to occur, the slower will be the rate. So there is a good relationship between the rate and the activation energy barrier. So now we understand that there is a strong correlation between activation energy barrier and the rate. For a process or reaction to occur, thermodynamic must be favorable and the kinetic must be fast enough. Then the process will be in a good direction, in good way it will occur. Suppose we can concentrate now on kinetic and thermodynamic control of the system. The potential outcome of a reaction or phase transformation is usually influenced by two factors. One, the relative stability of the products, that is thermodynamic factor. You can check in the second diagram or the diagram in the right hand side, the second diagram, where there is a relative stability of the product final state 1 or final state 2, that you can tell that thermodynamic factor. And the rate of the product formation, you can see it's, if you take that representative as the activation energy, then in the left hand side figure, the first figure, there the rate of the product formation is important to get the potential outcome of a reaction or phase transformation, that is kinetic factor. So any reaction, any phase transformation, there is a two futuristic control are there. One from thermodynamic point of view, another is kinetic point of view. So this is the thermodynamic and kinetic, both controls are there. Now we are going to understand the important statement and then associate equations. So already I discussed that to occur a process, there should be a scenario that it must overcome the energy maximum, that is activation energy barrier, and that is very important. And the higher the barrier, harder will be the scenario to process to occur or the process to be taken place. So generally the harder the process to occur, the slower will be the rate. So now we can concentrate that in order to occur a process, or in order to a process to be occurred or to be taken place, or a reaction to be taken place, the thermodynamics must be favorable. What does mean? That means del G must be less than 0 and kinetic must be fast enough. Otherwise, it will take long time. So one cannot even see or foresee when the product will come or when the product will seen. So that's why kinetics also must be very fast enough, so that and what does mean? The activation barrier will be less, small. So in general, the rate is having two factors. One is kinetic factor, one is thermodynamic factor. Although we used to know that thermodynamics does not talks about how the process is going to occur. It always talks about initial and final state. Still, the feasibility criteria is important in order to predict the rate. So say that feasibility criteria you are going to get from thermodynamic factor, and thermodynamic factor is directly related to del G must be negative, which talks about thermodynamically the process must be favorable. And then you can get an equation that is Arrhenius rate equation. Rate varies to e to the power minus activation energy by kT, and the T is in the absolute scale. And how you are going to get that? Suppose you are now understood that rate varies with two factors. One is kinetic factor, one is thermodynamic factor. And kinetic factor refers to activation energy, while the thermodynamic factor refers to del G, the driving force. So again, please pay attention. Kinetic factors refers to activation energy. I am repeating the statement that kinetic factor refers to activation energy, while thermodynamic factors refers to del G, that is the driving force. Now you have to understand the driving force. A thermodynamically favorable reaction or process means del G must be less than 0. Okay. And now you can say that highly driven process. That process is highly driven. So why is it so? The products are at lower free energy, more stable with respect to the reactant. And because of this, the reactants want to be converted into the product. So this is the thermodynamic criteria, and it is related to the driving force. So there is a strong desire of the reactants to be converted into the products. So that desire is represented by the driving force, that is del G. Del G is the G2 minus G1. G2 is, if it is represented, G is to product and G1 is the reactant. Or you can tell free energy of the product minus free energy of the reactant, and that should be negative. Now you have to find out the kinetic factor. So if you want to understand the kinetic factor, you have to understand the activation energy. So understanding of the activation energy is very essential. And it is that activation energy is basically the maximum in energy separating two equilibrium states. If you look at the previous figure, again I am going back to the previous figure. It is the maximum energy separating the two equilibrium states, and overcoming this barrier represents the bottleneck for the reaction to finish, thus a rate determining state. So to overcome this barrier, it's required to progress the reactions, the process, the transformation. The rate can be given in terms of transition state, often called activated complex. Sometimes we used to tell that activated complex, and the rate then can be represented by the transition state by considering the activation energy. The hump of the activation energy also indicates the high energy of a transition state or activated complex. It is very easy to understand. You can, if you pay attention, you can easily understand that the high altitude or high hump of the activation energy also indicates the high energy of a transition state or activated complex. That is at the top of the hump is so unstable, because the energy criteria, if you see, it is very high, so unstable. Still you have to go through that and overcome the activation energy barrier. So it is often they're confused. People become confused between thermodynamic quantities like free energy and kinetics ones like activation energy. There is a real confusion sometimes persists in students' mind also, that between the thermodynamic quantities like free energy and the kinetics quantities like activation energy. The reason, as per my understanding, that thermodynamics and kinetics are taught differently in a different subject, but it should not be. It should be taught in the same subject, and there will be a correlation. Although they are different, but they are having strong correlation. Today we can understand after completion of this lecture. So the free energies are average energy over a large amount of atoms. And also we know that definition of free energy is the energy, available energy of a system to do some work. So as a result of random thermal motion of the atoms depending on the temperature, why depending on the, already I told from the kinetic theory gases, 3/2 kT equal to half mv square. So that also, temperature also has a strong influence on the velocity of atoms, and that actually contributes towards the motion of the atom. So now we can tell that as a result of random thermal motion of atoms, the energy of any particular atom will vary with time, and sometimes it may be sufficient for the atom to reach the activated state, and one can name that thermal activation. And if you look at the kinetic theory, the rate of reaction is proportional to the probability to reach activated state. So thus you can write in the next slide, you can see that thus you can really write that rate varies to e to the power minus del Ga, which is activation energy by kT. This is a Arrhenius rate. This is an Arrhenius rate equation. This is a very significant equation for metallurgical transformation process. Not metallurgical, it is also chemical and any transformation process. This is a very significant equation, and this is a Arrhenius equation. Now, if you rewrite the equation in a logarithmic form, suppose logarithm of rate, then you will get del G by R into 1 by T. So that actually give you a linear relationship with the slope indicative of the activation energy. People used to do that in general way to understand what will be the value of activation energy. Now, again, I'll go back to previous slide to understand one important concept of catalyst. Suppose, for example, in a Haber process, finely divided ions serve as a catalyst for synthesizing the ammonia from hydrogen and hydrogen. So such reaction can hardly occur without the catalyst due to high activation energy. So what will happen? If you add finely divided iron, it will act as a catalyst and it will lower the activation energy barrier and make the process easily possible. The feasibility of process is there. Without the catalyst, the feasibility of the process is there because del G is negative for the process, because the Gibbs energy of the reactant, that is ammonia, is higher with respect to summation of the Gibbs energy of nitrogen and hydrogen. But there is a strong need to overcome the energy barrier, which is much higher, very high activation energy barrier is there. So in order to reduce that activation energy barrier, you have to use the catalyst, and that catalyst in this case eventually iron. So this is just an example. So this is a strong role of catalysis. And another example you can take, catalytic converter on process. What is it? This is typically composed of platinum and rhodium working as a catalyst to convert toxic byproduct of combustion, less toxic substance. What is more toxic with respect to carbon dioxide and carbon monoxide? You know, carbon monoxide is more toxic and carbon dioxide is less toxic. So if you react with carbon monoxide with certain things like NO, and then it will become carbon dioxide and nitrogen, which is less toxic. So this way you can get certain byproducts of combustion, convert them to less toxic substances. So all those cases you have to reduce the activation energy barrier. Now we have to find out one example which is thermodynamically favorable but kinetically unfavorable. What does mean? The feasibility of the reaction or transformation is there, but the activation energy barrier is so high that it is not kinetically favorable. So if you take graphite and diamond are both forms of carbon, but graphite has a lower free energy. Therefore, diamond is thermodynamically favorable to convert to graphite. If you check comparatively which one going to have higher free energy and which one will going to have lower free energy with among or between graphite and diamond, then you can say that graphite has a lower free energy. Therefore, diamond is thermodynamically favorable to convert into graphite. So if you purchase one diamond, it will become graphite. It should be, but it is not likely. However, this will never happen within your lifetime. It is always safe on your finger. Why is it so? Because transformation from diamond to graphite, although it is a thermodynamically favorable, is kinetically not favorable because the very high activation energy barrier. For the diamond to graphite transformation, getting to transition state probably involves, among other things, breaking all carbon-carbon bonds in diamond. Breaking those bonds demands huge amount of energy, implying very high activation energy. You should understand that. So sometimes there is a scenario where thermodynamically things are feasible or favorable, but kinetically it is not favorable because it is not fast enough so that one person can see the transformation in his lifetime. That's why graphite is stable, because that's why you can see the diamond is stable within our lifetime. So that's why diamond, although thermodynamically favorable to convert into graphite, but kinetically is not favorable. Again, another example, same way you can take, if you go for a reaction between hydrogen and oxygen, which is highly favorable exothermic reaction. And however, the reaction won't start spontaneously by itself unless ignited by a spark. Mixture of hydrogen and oxygen remains stable at room temperature. Ignition like burning cause the reaction. So that's why you need to have certain kind of energy in order to activate the reaction by crossing the activation energy barrier. So now we want to go for another thing, that is thermodynamic product and kinetic product. Suppose if you look at the reaction coordinates, so an energy that plot, in between there is one product, that is R, and you can tell that you want to understand how the control of kinetic is there or how the control of thermodynamics is there for two different cases. So if you name pk as a p suffix k as a preference for a under kinetic control and pt preference for a under thermodynamic control. So you see in the first figure the pt is much higher with respect to pk, so there will be a thermodynamic control. And if you look at in the second figure, pt is lesser with respect to pk, then you can see there is a preference of, there is a difference between the preference. So in this way we can understand, if you go for summarize our today's lecture, then you can get back to your get back for this lecture is like that. Thermodynamics basically tells us that a reaction should go if the products are more stable, have a lower free energy than the reaction, and the reaction has a negative free energy change. Negative free energy change, that is del G must be less than 0. And kinetics on other hand tells us how fast the reaction will go, though does not tells us anything about the final state of things once it gets there. It's not, it talks about only the energy barrier, the rate, the path, and all those things. And so combined of them is understanding of thermodynamics as well as kinetics are very essential, and their strong correlation is there. Although both are different, but they are related. They are really related. And thermodynamics, sometimes people then can ask a question, even that things can come to our mind also. that thermodynamics is not about dynamics. What does mean by dynamics? You always have a denominator, the time. Then you are going to talk about dynamics, but thermodynamics is not talking about time. It is not about moving or changing. It has nothing to do with the time. So instead of thermodynamics, one should tell that thermostatics. That is different thing, because since thermodynamics has a strong correlation with the kinetics, that's why the name is thermodynamics, not thermostatics. That is another reason we name the subject or name the area thermodynamics. Although it is not going to directly involve to with the time, it is not having the denominator, the time part, but still we are going to tell that thermodynamics, not thermostatics, because thermodynamics has a strong correlation with the kinetics, and that's why thermodynamics is named so. So hope all of you understand how thermodynamics and kinetics related, although they are different. Thank you.